Alrighty, so today we're going to be going over our third part of our analyses, and that relates to the moderator analyses. And the other name for that is subgroup analyses. And you'll notice that we'll be using those terms interchangeably. I prefer to use the word moderator, but I'll also use the word subgroup because when we look through how the data is run, it sort of makes a little bit more sense if you call it a subgroup, and we'll see why today. So the first thing that we want to do in this process, remember, when we're getting our data ready, we want to make sure that all our data is prepped like we talked about the week prior. So we need to make sure that any transformations that needed to have occurred have already been done. So if we've got a Cohen's D, we need to transform that to a Hedges G. If we've got a correlation R, we need to transform that to a Fisher's Z. And then if we're working with an odds ratio, we need to transform that to a log odds ratio. And then you want to make sure that you have the inverse variance weight for each item. So that's that W column that we have worked with the past several weeks. And we want to do some basic analyses. So we want to get that mean fixed effect size and the associated statistics that come along with that. And we also want to get the mean random effect size and also those associated statistics with that. Because even if we end up using the random effects model, we still need to generate both the fixed and the random effects models. And then we'll run our heterogeneity analysis. So at this point, we're assuming that we've gotten this far in the analysis process. And so now onto our moderator or subgroup analysis. So we're going to talk about these three things today. So the first one is looking at fixed effects. So we're going to do two different tests. So first we'll look at a z-test, which is pretty much an analog to the t-test. A z-test is basically comparing the two effect sizes, so the effect size for group 1 and comparing that to the effect size for group 2. The z-test is actually useful to us when what you're comparing is two groups. So if you're looking to find if there's a difference between men and women, or if there's a difference between setting, like treatment settings, so institution versus community, things like that, the z-test is very helpful for that. The other test that we're going to talk about is an analog to the one-way ANOVA. And so if you assume that you have more than one group, you can also do it with two groups. And you'll end up getting to the same place that you do with the z-test when you do the analog to the one-way ANOVA. And just to comment again, I know that this was mentioned last week in the heterogeneity lecture, but the analog to the one-way ANOVA, things are slightly different because we're not working with primary level data. Instead, we're working with study level data. And because of that, it's very much like an ANOVA, but it's not exactly the same. So you wouldn't be able to just go plug your effect sizes into SPSS and run it like you would a normal ANOVA. And so that's why we're referring to it as the analog of the one-way ANOVA. And then we'll do the same things for the random effects model as well. And then finally we'll talk about the summary data that we get for each group, and then the total. So the first thing that we need to do in order to create that fixed effect in any sort of moderator analyses, we need to create the summary data for each of our subgroups. And so now we're using, again, the Wilson PowerPoint example. We've been looking at this the past several weeks in the lectures. And so now we're looking at the same 10 studies from the Wilson PowerPoint example, but we've grouped them into two different groups. And so you can see here the first 6 studies are grouped in group 1 here, And then the last 4 studies are grouped in group 2 down here. And so we're just going to add a couple of rows in between these groups so that we can create sums to the individual groups themselves. And so kind of like before when we were computing our basic summary effect size data overall for our study, we created a sum for each of these 3 columns. So now we're going to do that, but we're going to create 2 sets of sums. So we need a set of sums for group 1 and then another one for group 2. And we'll actually end up with a 3rd row down here below group 2 that is the sum of group 1 and the sum of group 2 as well. So it'll end up being this sum plus this sum equals that 3rd sum. And so we'll need to calculate those 3 sums for each one of our groups. And that's the sum of our weights, the sum of the weight times the effect size, and the sum of the weight times the effect size squared. And right now we're only showing that this has 2 subgroups, so group 1 and group 2, but you could also do more than 2 subgroups if you have more categories that you're wanting to look at and compare them for the same variable. And it'll create a row with totals for each. Alright, so if we are to use the data from the last slide, so those 3 sums that we're calculating, we end up creating the summary data. So we have the data for group 1, we have the data for group 2, and then we also have the total effect size data. And if we were to just look at this table, it looks like there's a definite difference between the effect size for group 1 and group 2. So group 1 is 0.2984 and group 2 is negative 0.0277. So you can see that those are pretty different from one another. And although this effect size, this total 0.1549, is partly in between these 2 effect sizes, this total effect size doesn't really seem to be capturing the spirit of what's happening in either group 1 or group 2. And so the next thing that we want to do is look at our Q data. All right. So here, the z-test, again, is an analog to the t-test, and we need 3 different pieces to do a t-test. We need the difference value, we need the standard error for difference, and then we can calculate our z based on that. So the difference is going to be the mean effect size for group 2 or group B minus the mean effect size for group 1 or group A. So group 2 minus group 1. And then we'll have the square root of the variance for the mean effect of A plus the variance for the mean effect of B. And you'll see that I've taken these numbers from the last slide. So negative 0.0277 and positive 0.2984. So I just pulled those from each group. And so then we need the variance. So we didn't have the variance, we just have the standard error. And so I took the standard error and squared it. So 0.813 squared plus 0.0917 squared is the square root of 0.015, which equals precisely 0.1255. I know you can't see the 55 at the end, but it's 0.1255. And then we take this first number, the difference of our effect size, which was negative 0.3261, and we divide that by the standard error of the difference, and that ends up equaling negative 2.66. And so if you look that value up in a z-table, you'll definitely find that that value is statistically significant. Okay, and so now moving on to the analog for ANOVA. So here we want to remember that Q is equal to this lovely formula here that we have on top, which looks much more wicked than it actually is. And it's basically the sums that we've already created. So here we have the sum of the weight times the effect size squared, which is the third column of the three sums that we created. And so, let's see, we end up with 19.90, and then we subtract 45.10 squared, and we divide that by 151.15, and for group 1, we came up with a Q value of 6.44. We do the same for group 2, and we end up with a Q for group 2 of 1.25. And so if we go back to that table to look at the Q values, Q for group 1, 6.44, yes, that's right. And then Q for group 2, 1.25, yes, that's correct. And also the Q total here we see in this table is 14.76, which we'll actually need a little bit later on, so we will look at that soon. All right, so now when we do have an ANOVA, we normally have a sum of squares within, and we also have a sum of squares between. But here instead, we're actually going to have a Q between and a Q within. So our Q within is going to be the amount of Q, which is our heterogeneity, of group 1 plus our Q of group 2, and that gives us a total of 7.69. And the degrees of freedom that goes with that is the number of effect sizes minus the number of groups. So we had 10 studies in the Wilson PowerPoint example, and then we're subtracting 2 groups, so we get a degrees of freedom of 8. And so the difference between the Q total and the Q within is going to give us the Q between. So the Q total is 14.76. Remember, we saw that on this slide back here. Our Q total, 14.76. Minus our Q within, which is 7.69, which we just found up here. And that gives us our Q between, which is 7.07. And so what this Q between is looking at is there a significant amount of heterogeneity that's attributed to this between groups difference? So in other words, do we have some significance between the difference? And so our Q between in this case is 7.07. And the degrees of freedom that goes with that is the number of groups minus 1. So in that case, we had 2 groups minus 1, and that gives us a J of 1. And we see that that is definitely statistically significant. So our Q between is 7.07 with a degrees of freedom of 1. And that is statistically significant because we see P is less than 0.05 here. Our Q within is 7.69 and our degrees of freedom is 8. This is actually not statistically significant here because we can see that P is greater than 0.05. We see our Q total is 14.76 with a degrees of freedom of 9. This also is not statistically significant because our P is greater than 0.05. So at this point, because Q between is 7.07 with 1 degrees of freedom, and that is statistically significant, our grouping variable is accounting for a significant amount of the variability in effect sizes. So there is something statistically significant going on, and that grouping variable is a significant contributor to the difference in the effect sizes that we're seeing. So let's move on to the random effects model. So we're going to do basically the same process, but we're going to do it in the random effects model. We need to acquire the 3 basic sums that we did just like last time. So we're going to need the sum of the weights, the sum of the weight times the effect size, and then the sum of the weight times the effect size squared. And this time, remember that we're doing it with the added calculation of the variation component that gets added in with the weights for each study. So that little bit of tau squared that gets added into each study. So we're going to calculate those 3 sums for each of our groups, group 1 and group 2. And then the total summary effect size is down below here on this 3rd row. And so now we're going to use this set of data to create our random effects summary group data. And so we have our mean effect size and our total effect size. So we have that for groups 1, group 2, and for the total. So we can see that group 2's effect size was negative 0.2471, and group 1's effect size was positive 0.2834. So that's pretty close to 3 there. And so just looking at those two, we can see that there's a huge spread between these 2 groups in the effect size. And if we look at the total effect size, we see that it's positive 0.2609. This total effect size ends up being closer to the higher end this time. You can see that the total is closer to the higher end of the effect size that we're seeing. So we're going to do the same exact process for the z-test that we did before, and we're just going to be using the random effects data here. So we're going to get the difference here, so we're going to take the mean effect size for group 2 or group B, and we're going to subtract the mean for group 1. So we're going to take negative 0.2471 and subtract positive 0.2834, and that gives us a negative 0.5305. Variance, which we don't have, we're going to square the standard error in order to get the variance. And so we take 0.3599 and we square it, and add 0.4614 and square that, and that gives us 0.5852. And that's very different from what we had before. So the difference between our mean effect sizes isn't substantially different than it was before. So negative 0.3261 was the fixed effect difference. But notice that our standard error was 0.1255. So from 0.1255 to 0.5852, that's a drastic difference in the standard error. So we have even more difference between our means this time. We have so much more variance. Our standard error is so much larger this time. And we actually end up with a much smaller z-value in the random effects model. So we take the negative 0.5305, which is the difference between the mean effect sizes, and then we divide that by our much larger standard error, 0.5852, and that leaves us with a much larger difference for z of negative 0.9065. So this is saying that for the z-test, there's no statistically significant difference between our groups. And so let's see if the Q analog ANOVA fares out the same way. So we're going to do the same thing. We're going to take those lovely sums. We're going to stick them in this magical formula. And in this case, Q for our group 1 is 5.46, and our Q for group 2 ends up being 1.58. And we're going to see if that matches what came out for the Q. Yes, we've got 5.46 and 1.58, so those Q values match. And remember, our total Q is 8.307, which we'll see in just a few minutes. And so we will go ahead and calculate our Q within value. So we're just going to add up the Q values for our two groups, and we end up with a Q within of 7.04. Our degrees of freedom is exactly the same, so our number of studies or number of effect sizes minus the number of groups, so 10 effect sizes minus 2 groups gives us a degrees of freedom of 8. And our Q between is again that total value of Q minus the Q within value. And so this time the Q ends up being 1.27. And that's not going to be statistically significant. We have a very small Q and our degrees of freedom is 1. So we have our Q between of 1.27 and our Q within of 7.04, and our Q total is 8.31. And you can see that looking at the p-values, none of these Q values are significant because they are all p is greater than 0.05. So in this instance, our grouping variable is no longer accounting for any of the significant variability in our effect sizes. And that's because the random effects model is allowing for some of the variability in the effect sizes to be accounted for by the fact that we're just expecting there to be some random element to that. And so that parses out a bit of the variance. So it's already been accounted for by a random effects model. So there's probably less variance overall. So we have less variance to deal with here. And just as a discussion point, you'll notice that throughout the term with the articles that you guys have been looking at, the published articles, peer-reviewed published articles each week, you'll notice that how some of the researchers have been handling this has been they typically oscillate between choosing or between looking at a fixed effect model and a random effects model, and they're calculating both and they're looking at both, kind of choosing which one they should look at. And very clearly in our readings from Borenstein, actually a number of chapters ago that we already came across, they were very clear that you're supposed to decide which model you use based on the theoretical assumptions of your data. But important to note, the old way of doing that, which is outlined in the Lipsy and Wilson text, was looking at that by running the fixed effect model, checking for the heterogeneity, and if the Q ends up being statistically significant, then you go ahead and run a random effects model. And it's still clear that this is still happening in the literature today. This is not something that I want you to do. You're actually going to follow the Borenstein et al. Very closely. And truthfully, for any sort of psychotherapy research, we're going to expect it to vary a lot from group to group, from clinic to clinic, from region to region, from variable to variable. So we're not going to be looking at a fixed effect model for any topics you'll be researching related to psychological data. We're always going to use the random effects model.